Hello everyone, this is Sarvesh, lecturer in Civil Engineering, Government Polytechnic, Station Gun. And the course is Reinforced Concrete Structures. The topic is Design of Continuous Beams and Slabs. So the main objective of this lecture is after completion of this lecture, you are able to know how to solve how to design a one-way slab, continuous one-way slab by limit state method as per the coefficients proposed by IS 456 2000. Right. So in this we are going to solve a simple example problem how to design the continuous one-way slab. Before going to the topic, just recap what we were discussed in last class. So in last class, we were discussed about the design procedure for continuous slabs and what are the different steps involved in design of continuous slabs. So we have discussed each and every step. That means the calculation of uh, dimensions of the member slab and effective span calculations and determination of loads on the slab and calculation of shear forces and bending moment. Then we have calculate how to calculate the reinforcement for each section. Then what are the specifications of IS coded provisions in design of continuous slabs? Then how to check for stiffness and developmental and shear. So these are the things we were discussing class. What are the limitations and coded provisions? Everything we have seen in last class. Now we are going to apply those steps in present lecture. Right. So for that, I have taken a problem that is design a design a continuous one-way slab for an office floor. The slab is continuous over beam spaced at 3.5 meter intervals, and the width of the beam is 230 mm. The superimposed load is 3 kN per meter square. And floor finish, FF means floor finish is 1 kN per meter square. And use M20 grade concrete and FE 415 steel. So this is the data they are given, and in problem directly they said it is a one-way slab. So you no need to check whether it is one-way slab or two-way slab, because directly in problem it clearly says that it is a one-way slab, right? And the slab is continuous over beams spaced at 3.5 meters. So that means suppose this is a continuous slab, and let us say the beams spaced at a distance of 3.5 center to center, right? So that means the distance between from this center to this center is 3.5 meters, right? And the width of the support, that means this width is 230 mm, right? So this is a plan of the slabs. So yeah, already. So same thing here also this stage not clear. So therefore, yeah, this same thing, right? Next is what you have to do is just write down the given data. What is the data is given? So that means I can say it is center to center distance between the beams, right? So width of the beam is 230 mm, FCK is 20 MPa, and F of is 4. And superimposed load is 3 kN per meter square. This is 4 to 1 per meter. So what we have discussed in last class. So while designing, first you need to determine the dimensions of the slab. That means the depth of the slab. So for slab design, as I told earlier, we will consider 1 meter width, right? In other direction, we will consider 1 meter width, and we need to assume the depth of the member. So generally, the depth of the member in continuous slab can be assumed for L by 25 to L by 35. So here I am assuming that the effective depth of the slab is L by 30. So that is 3500 by 30 is 120 mm. Right? So it is not compulsory you have to take only L by 30. It is just assumption. So based upon your experience, you can assume or you can directly take some value based upon your experience. Right? So I have considered L by 30. You can take it as L by 25 or L by 35, whatever the value feasible for you. So based upon that, you can assume. And one more thing is I am assuming that the effective depth. Otherwise, you can assume overall depth of the slab installed. Right? So anyway, either way you can assume and find out the other value. So here I am assuming effective depth as L by 30. So I got it as 120 mm, and again I'm assuming the effective cover directly instead of assuming the clear cover and diameter of the mask. So directly based upon the codal provisions, I'm assuming that the 25 is the effective cover. Therefore, the overall depth of the slab is 145 mm, right? So now the dimensions of the member slab is finalized, and width of the slab, that means B is equal to considering 1 meter width of the slab in other direction, right? So the next step is you need to determine the effective slab. So here it is a one-way slab, so you have to calculate only shorter span direction, right? Just clear. Next is, yeah, calculation of effective span of each panel. Here, for each panel, I told that the panel is nothing but this one is one panel. This is one panel, and this is also one panel. This is one panel, right? So, clear span is nothing but what? The inner to inner distance between the supports. That means the distance from here to here. How to calculate that? That should be calculated. So we know the distance from this is 3.5 center to center. So minus this is 230 by 2 minus this is 230 by 2. Right? We will get the inner to inner. That is 3.5 minus 230. We will get 3270 mm. This is the clear span between the beams. And as I told earlier, for continuous slabs, the effective span calculation is depends upon the width of the support. So as per ISO 56000, if the width of the support is less than the 1/12 of the clear span, then the effective span can be calculated same as your simply supported beam or slab. If it is greater than the 1/12 of the clear span or 600 mm, whichever is less, the calculation method is different, right? So that you need to determine before calculating the effective span. So the 1/12 of clear span, that is 3270 by 12, what is that? 372.5 mm. So therefore the width of the support is 230 mm. So 230 mm is less than the 272.5. So therefore the effective span can be determined same as simply supported beam. That means the least of the following, that is the center to center distance between the supports or clear span plus effective depth, whichever is less, right? So same thing I have calculated here. So this is a clear span, center to center distance between the support is think I would like to erase only one thing. Yeah, because yeah, I think it's over there. Let us. Yeah. So the center to center distance between the support is 3.5, as I shown in figure just now. And clear span plus effective depth is 3.27, that is the clear span, plus effective depth is 120, that is 0.12, 3.39 meters. So least of these two is 3.39. So this is now this is our effective span. So therefore our effective span is 3.39 meters. After determining the effective span, the next step is we need to determine the loads on a slab. So loads are calculated per width of the slab, that means per meter length of the slab. So the first is self weight of the slab, that is 0.145 into 25 into 1 meter distance, that is 3.625 kilonewtons per meter square, right? The floor finish is 1 kilonewton per meter square. And this is the floor finish. This is also considered as fixed because it has to be there throughout the lifespan of the slab. So that is also considered as fixed. So then calculate the total fixed, that is dead load is fixed because it will appear uh, throughout the life of the uh, slab, right? So these two are fixed, that is uh, 1 plus 3.625 will get 4.625 kilometer meter square. Then the imposed load, that is not fixed, that is 3 kilonewton per meter square. And these are the working loads. You need to determine the um, factor loads by application of partial safety factor for loads. So the partial safety factors for live loads and dead loads is 1.5. So the total load fixed, that is 4.625 into 1.5 will get 6.94 kilonewton per meter square. Similarly, for not fixed, it is 3 into 1.5 will get 4.5 kilonewton per meter square. So these are the factor loads. So based upon this, you need to determine the shear forces and bending. So next step is determination of shear force and bending. So this is a method which is these are the bending moment coefficients proposed by IS 456 2000 for continuous beams and slabs, right? So, but before using these coefficients, you need to check three conditions. As I told earlier, also again I am repeating. The three conditions is the beam or slab should consist of minimum three spans, right? So next one is it should consist only the UDL loads. So in our case, it has more than three spans and it consists of only UDL loads. Next important is the difference between any two uh, spans. The difference between any two spans should not be greater than 15% of the longest span. That means the difference between any two spans should not be greater than the 15% of the longest span. So in our case, all spans are equal spacing. So therefore, the difference is less than 15%. So these coefficients are applicable, right? So here, generally, here there are two types of movements: span movements and support movements. So actually, in practical, you have to calculate all the bending moments by using this coefficient, out of which you have to take the maximum one. That is one method. Otherwise, you have to calculate all the bending moments and corresponding um, steel has to be determined for at each place, right? And another method is simplest method for reducing the calculation cost directly. I can take it as maximum bending moment, span moments, maximum span moments, and maximum support, right? Because why I am taking corresponding to maximum, if whatever the member we are going to design, so I will check corresponding to the maximum. If they are safe in maximum, automatically it will become safe in other cases, right? So that is why for span moments, I can calculate maximum. So from the coefficients, I can easily identify where I will get the maximum value. So here the coefficients for this is 112, 110, 160, and 112. So obviously these coefficients higher than this one. So you will get the maximum span moments at near middle of end span. So therefore, I will use these coefficients and determine the, I can calculate the maximum span moments, right? Similarly, the maximum support moments will occur. So out of these two, these are the maximum, right? So I will get the maximum bending moment at this place where it is at support next to the support, right? So directly I am calculating the, yeah, these are the shear force coefficients we'll discuss while we checking for shear force. Yeah, right here. So the maximum out of which another one is you need to check for depth, right? So that should be checked corresponding to the maximum. So the maximum is occurred at support next to the end support, that is mu max, that is negative bending moment. As I told earlier, if this is a continuous beam or slab, right? The bending moment diagram approximately something like, or you can say deflection. So obviously, at middle of each span, you will get the sagging bending moment. At support, you will get the Haugen bending moment. That is negative bending moment. This is positive bending, right? So here the maximum is negative bending moment. That is minus WU L square by 10 minus WU L square by 9. So if you substitute the values, minus 6.94 into 3.39 square by 10 minus 4.5 into 3.39 square by 9. So the maximum bending moment you will get 13.72 kilonewton meter. This is Hagen bending. And maximum span moments occur at middle of end span. That is WL square by 12 plus WUL square by 10. That is 6.94 into 3.39 square by 12. This is not minus, this should be plus. And 4.5 into 3.39 square by 10, you will get 11.82 kilonewton meter. This is the maximum positive bending moment, that is span, right? So after calculating the shear bending moment, then you can go for calculation of check for depth, right? That means in first step, we have assumed the dimensions of the member and especially the effective depth of the member or slab. So that you need to check whether the assumed dimensions are sufficient to resist the bending moment which are developed between the beam. And that can be checked by equating your maximum bending moment equal to mu limit. Mu limit is nothing but the moment of resistance corresponding to the uh, balanced section. That means the limiting depth of neutral axis, that is XU max. And that XU max can be determined from IS 456 2000 based upon the grade of steel, that is XU max. For Fe250 it is 0.53D, for 415 it is 0.48D, and 500 0.46D. And you can calculate the mu limit, and if you, that mu limit is nothing but what? new limit equal to 0.36 dx max t minus 0.42 max, right? So in this equation, just substitute x max. So for in the present case, our grade of steel is Fe415. So substitute x is equal to 0.48 here and here, and simplify it. You will get this equation. This is NU limit, and this NU limit is equal to the your maximum bending moment. What is the maximum bending moment? So this is the your maximum bend. Equate and find out the depth required, right? So from this, if I calculate this simplifying equation, that is D is equal to the root of 13.72 into 10 power 6 by 0.138 into 20 into 1000. Here D is 1 meter we have considered, that is 1000 mm. So if you substitute the D required, D is unknown. Remember, don't substitute whatever D we have assumed in first case. Here you need to determine the D required to resist this much of weight, right? So that we got it as 70.5 mm, and then you need to compare it. So this is D required, and what is D provided, right? So your D required, your D required should be less than D provided, right? Because whatever the D required to resist this much of bending moment, if you have provided greater than the required, then it is safe. So in this case, it is safe. The 70.5 is less than the 120 mm. So whatever you have provided is more than the required. So it is safe. Suppose if D required is greater than the D provided, that means your beam will fail. So you need to redesign your section by increasing your depth of the slab or thickness of the slab. So it is a repetitive process till this condition should be satisfied. That is, D required should be less than the D provided, less than or equal, right? So after satisfying this, then you can go for further steps. The next step is calculation of reinforcement, right? So the reinforcement is calculated for different sections or critical sections. So here, first the reinforcement is calculated at supports. So at support, the maximum bending moment is 13.7, right? So mu max equal to 0.87 f of y into a of st into d into 1 minus f of y into a of st by fck into d, right? So this is not a new formula. It is derived from the basic formula, that is mu is equal to tension force into lever arm, that is 0.87 into f of y into a of st into lever arm is 3 minus 0.42, right? So don't substitute the XC max whatever we have used for checking the depth of the depth required, right? Because that is only for the purpose of checking, right? So you should not use that XC max here. Here you need to use actual depth of metal axis. The reinforcement should be determined corresponding to the actual depth of metal. What is the actual depth of neutral? How to determine the actual depth of neutral axis? The actual depth of neutral axis can be determined by equating the compressive force equal to tension force. That is 0.36 FCK into E into 0.87 f. So from this equation, X2 should be calculated in terms of A of ST, right? And that A of ST is should be substituted in this equation XU. So you will get is derived from the basic only. If you have a confused with this equation, you directly use this equation. That means mu is equal to tension force into lever and x to substitute here, and you can calculate the area of steel required at supports, right? And if you substitute the values, that is 13.72 into 10 power 6 equal to 0.87 into 415 area of steel into 120, and substitute these values, and if you solve this equation, the area of steel will get as 336.3, right? And directly you should not provide this one. You need to check corresponding to the maximum and minimum as per IS 46000. The minimum main reinforcement for slabs is for Fe415 it is 0.12% of BD, and for mild steel it is 0.15% of BD. So here our grade of steel is Fe415, therefore it is 0.12% of BD. So that is 0.12 into our B is equal to 1000, B is equal to 145 by 100. Then we will get minimum area of steel is 174 mm square, right? Similarly, calculate the maximum reinforcement. As per the codal provision, the maximum reinforcement in slab should not be greater than 4% of B. That is 4 into 1000 into 145 by 100. You will get 5800 square. And whatever your AST required should be greater than the minimum and less than the maximum. So check it. So 174 is 336.6 is greater than 174, less than 5800. Therefore, it is satisfied. So then, if it is satisfied, then you can go for further steps. That is determination of spacing. So here you need to determine the spacing instead of number of bars, because in beams we need to calculate the number of bars. Here you need to determine the spacing. So assuming 10 mm dia bars, then the spacing required is small AST by capital AST into 1000, that means 1 meter width. So that is 78.54 by 336.3 into 233.5 mm. So this is the spacing required to resist that much of bending, right? But you cannot provide directly this spacing. There are some codal provisions for providing the spacing between the main bars. So that is the maximum spacing should not be greater than the 3D or 300 mm, whichever is less. So for 3D, that is 3 into 120, you will get 360 mm and 300 mm. So now you have three spacings. One is from the calculation, another two is from the codal provision. Out of these three, you can provide the minimum. So therefore, it will satisfy all the conditions. So which one is minimum? 233.5 mm. So therefore, provide 10 mm dia bars at 230 mm center to center spacing, main bars at supports, because whatever the bending moment we have calculated, that is at supports, right? So therefore, after calculating the reinforcement at support, similarly you need to calculate the reinforcement at midspan also, because the bending moment is different for supports and midspan. So here also same thing, you can use same formula for determining the area of steel. This formula and substitute the values. So that is the at midspan the bending moment is 11.82 to 10 power 6 Newton meter. And if we solve this equation by substituting the values in this equation, and we get the area of steel required to resist this much of bending moment is 287 square. So similarly, you need to check corresponding to the maximum and minimum steel. So that is the minimum steel means main reinforcement is 12%, 0.12% of BD, that is 174 mm square, and for maximum 4% of BD, that is 5,800 mm square. And your AST required should be greater than the area of steel, minimum area of steel, and less than the maximum. So 287 is greater than 174 and less than 5,800. So therefore it is safe. You can provide AST report. So same thing, you can assume the diameter of the bar and determine the spacing required. So that is assuming 10 mm dia bars. So therefore the spacing is 273.7. Right. And as per IS 456 2000, so this is also a main reinforcement. Remember, this is not a distribution reinforcement, right? So therefore, same specifications occur here. That is, the maximum spacing should not be greater than 3 times of D and 300 mm, whichever is less. So 3 times of D is 3 into 120, that is 360 mm, and this is 300. So out of which you can provide least. Which one is least? 273.7 is the least. So therefore, provide 10 mm dia bars at 270 mm center to center spacing. Main bars at mixed pack location. Right? So this is how you need to determine the uh, main reinforcement in one-way slabs, in continuous slabs. So after this, you need to determine the distribution scale because this is provided in shorter span direction. So that main reinforcement should be provided in shorter span direction, and the distribution still should be provided on sorry, longer span direction, right? So that means just I would like to show the diagram. So suppose if this is your one panel, for example. So the steel, so this is a shorter span. So here it is provided like this. These are the main reinforcement, right? And in another case, you need to provide this is the longer distribution in this direction, right? Right. So now the calculation of distribution reinforcement. Now calculation of distribution reinforcement. The distribution reinforcement is provided in longer span direction. And as per the codal provision, the distribution reinforcement should be provided as minimum reinforcement. So the minimum reinforcement is for FE4156 is 0.12% of PD. It is by 100, right? So therefore it is 174 mm square. So same thing, you can assume the diameter of the box. That is, here I am assuming 8 mm diameter of the box. Then spacing required is small a by capital A 2000, that is 289 mm, right? So therefore, then there are some other codal provisions for distribution reinforcement, right? As per IS 456 the distribution reinforcement should not be greater than the 5 times of D or 450 mm, whichever is lesser, right? So 5 times of effective depth, that is 5 into 120 will be 600 mm, and 450 mm. So whichever is less. So out of these three, now you have three spaces. This one, and this one. Out of these three, which one is minimum? So this one is minimum. So provide this spacing, so it will satisfy all the conditions. So therefore, provide 8 mm dia bars at 280 mm center to center spacing for distribution reinforcement along the number. direction. So like this, you need to determine the distribution line, right? So we have calculated the main reinforcement at supports and at midspan. Then we have calculated the distribution line. So this is how you need to calculate the reinforcement required. Then the next step is you need to check whether your design is safe corresponding to the stiffness and shear or not. And in development that also as we discussed in last. So for calculation of uh, check for thickness. Uh, as per IS 456-2000, for continuous beams and slabs, the allowable L effective by D ratio equal to 26 into F1. That is, the F1 is nothing but your factor, modification factor. Yeah, yeah. As per the codal provision for continuous basic values, 26 into F1, where F1 is the modification factor. And that modification factor is depends upon the percentage of steel provided at midspan and f of s value, right? So if you know those two values based upon the curve which is proposed by IS 456-2000 from this curve, you can determine the modification factor and multiplied with the basic value, you will get the allowable L effective by D ratio value as per IS 456-2000, right? Then you just calculate the actual L effective by D ratio for your design slab. Then check whether it is exceeding the permissible limit or not. Right? If it is exceeded, then you need to redesign your slab. That means you have to go to your first step, uh, then increase the depth of the beam, sorry, depth of the slab, then calculate the effective span and loads, and again calculate the bending moments and reinforcements, etc. And then again come to the check. And this has to be done till the condition is satisfied. That means the actual L effective by D ratio should be less than or equal to the allowable value. Right. So for this, so in this case, the basic value is 26 into F1, and whatever the percentage of steel provided at midspan is AST by BD. So I got it as 20.28 percentage. And f of s, that is f of s value is this one, 0.58 into f of I into area of steel required by area of steel provided. Generally in slabs, basically what we will do is this ratio value in slabs we will take it as 1, because see, uh, in beams what happens, while calculating the number of bars, right? So if the number of bars is some, let us say 3.6 or 3.7, then what we will do, we will equate to, we cannot provide 3.6, 3.7, right? So directly we can round it up to 4 bars, right? So therefore, the area of cross section of steel required is corresponding to this 3.7. What you have provided is this one, right? In beams. But what happens in slabs, so instead of calculating the number of bars, here we have calculated the spacing. So that means the area of steel required by area of steel provided is more or less equal to 1. So that is why in slabs, this ratio is, can be considered as 1, right? So therefore, then f of s value is equal to, becomes as 0.58 into f of y. So that is how much we got it as. I got it as, see, I have considered 1, right? So 240 Newton per mm square. Then the percentage of steel is 0.28 and f of s is 240. Then what is the value of modification factor? 0.288. This is 0.4. That means this is 0.2. So 0.288 means somewhere else here, approximately point. And 240 is directly this state, right? So if you use this somewhere else here, this is your 240. So from here you can write just approximately I'm drawing. So it is approximately is 1.2, this is 1.6, so this is 1.4. It is just nearer to 1.5. Right? So if you draw exactly, you will get the exact value. So from this, I got it as 1.55. Right? The modification factor I got it as 1.55. So therefore, the allowable value for L effective by D ratio is 40.3, and the actual L effective by D is, that is 28.25. Right? That is 3,390 by 120. You will get 28.25, which is less than the allowable value. Therefore, it is safe. That means whatever your design slab, that is safe against stiffness. If it is greater than, then you need to redesign your section by changing the or increasing the depth of the slab. Right. So this is how you need to design your continuous one-way slab. So after that, you have to draw the reinforcement details. Right. So this is yeah. For this, I would like to conclude what we were discussed till now. Just summarize what we have discussed till now. So today class we have discussed about the design of the one-way slab based upon the given data. We have calculated the um, dimensions of the member, that is depth of the slab by assuming the uh, L effective by D is 30, right? So based upon that, we have calculated the overall depth by assuming the effective span. Then we have calculated the effective span. So as I told earlier, the effective span is depends upon the width of the support. So we have checked it. So our width of the support is less than the 1/12 of the clear span. So therefore, the span effective span should be calculated as same as simply supported. So therefore, then we have calculated the working loads and calculated the factor loads by application of partial safety factors. So after that, we have calculated the shear forces and bending moment based on the method proposed by IS 456-2000, that is from table number 12 and 13, right? Then based upon the bending moments, we have checked our dimension, that is we have calculated the depth required, and we have checked whether our depth required is greater than or less than the provided. So in our case, we got depth required is less than the depth provided. So therefore, we have calculated the reinforcement for supports based upon the support moment, and then we have calculated the reinforcement at mid span based upon the mid span, and based upon that we have calculated the area of steel required. After that, we have calculated the um, distribution reinforcement, that is as per IS 456-2000. The distribution reinforcement uh, should be minimum. That means minimum reinforcement should be provided as a distribution reinforcement. So that is for Fe415 steel or HYSD bars, the minimum steel in slabs is 0.12% of the. So we have provided the minimum reinforcement as a distribution reinforcement, and we have calculated the spacing required. And then we have the spacing required for distribution reinforcement as per IS 450-5000. The maximum spacing should not be greater than 5 times of T or 450 whichever is less. Then after that, we have checked for stiffness. That means we have calculated the allowable L effective by D ratio, that is for continuous using slabs, which is 26 into modification factor, and the modification factor calculated should be percentage of steel provided in midspan and above span. So based upon that, we have calculated and we have checked corresponding to our actual LF by D ratio. And our LF by D ratio is much less than the permissible value, so therefore it is safe. So this is what we have done in today's lecture, right? So next class we will discuss another topic. So thank you.